Alright, in the previous segment of the video I'd found the acceleration. I put all those calculations up here. We can keep them on the side if we want to reference them again. But at this point we now know this acceleration, and so we'll go ahead and write that number in, 11.82 meters per second squared. And that leaves us with only two motion unknowns, the velocity that we want, which is at point B, and then the time. And so I'm going to, I think I'll try to use the displacement formula, delta y from A to B will equal VA, time from A to B, plus 1/2 the acceleration from A to B times the time from A to B squared. And then put in the appropriate numbers. 1.2 meters equals 0 time from A to B plus 1/2 acceleration from A to B, which we know is 11.82 times the time from A to B, and that's squared. And solving for the time from A to B gets you 0.45 seconds. Well, that should allow us to easily calculate the velocity at point B. We can use the acceleration definition. Velocity final minus velocity initial for that segment divided by the time for that segment. And then putting in the numbers. This is 11.82 equals VB minus 0 over 0.45, and that means VB is equal to 5.3 meters per second squared. Okay, so these are the quantities we found so far. Now what we like to do is figure out how fast it's going here, assuming that now that we know this, that's going to tell us something. The force is on this thing is constantly changing direction, and so the acceleration of rising is going to be changing, and that makes it difficult to use a forces approach. But what we can do is use an energy approach. An energy approach might go something like this. We can draw a pie chart here for B and a pie chart here for C. And then to B, let's draw the level there. H equals 0. What's the height equals 0? So at B, it's storing energy only kinetically. But then at C, it's storing energy kinetically because undoubtedly it's still moving. But it's also high above that level, H equals 0, so it's storing energy positionally. And there's nothing in the problem that indicates we should consider friction or air resistance. And then from this we can build a conservation of energy equation. KE at B equals KE at C plus PE at C. This is going to be 1/2 times the mass of the electron times velocity squared at B. This is going to be 1/2 the mass of the electron times velocity squared at C. And this is going to be the mass of the electron times the gravitational field constant times its height. Playing a little algebra trick here, you'll notice that m is in each term, and so if we divide the equation by m, we create a much simpler equation to work with. This will be 1/2 times 5.3 squared equals 1/2 VC squared plus, and this will be 9.8 times a height of 0.45 meters. That's because this height here is the same as the radius, which is given as 0.45 meters. That gets us V sub C to be pick it up in the next segment.